Hello, everyone. Thank you very much for joining us for another VES-Artex Academy webinar. Today, we're talking about artificial heat stress with Dr. Matt Brady. Dr. Brady is one of the veterinarians that we work with here at VES-Artex. If you have any questions throughout the presentation, you can ask them through the question and answer box at the bottom of your screen, or you can ask them during the chat box. We're going to be answering questions towards the end of the presentation. And at the very end, when you log out, we have a very short survey, and we would really appreciate it if you would take the time to fill that out. So now I'm going to turn over the floor, and Dr. Brady, the floor is yours.
All right, thank you. So today I will be talking about what I have called artificial heat stress. So quick little bit of background on me. I went to vet school at the University of Minnesota, and straight out of vet school began working for VES, and felt that it was a good way to be able to prevent disease rather than treat disease. So I'd rather see animals not have disease and be able to make more money for a producer. So we'll talk about what is artificial heat stress as I define it. I kind of came about this term after a few case studies that we did last summer and some of the results from that. And so we'll go over the background of those case studies, the design, the results that we got, and then kind of a little bit of a comparison of the results. Because they were on different farms, you can't directly compare to one another. You know, oh, these cows didn't go into heat stress, but these cows did, therefore one farm's better than the other. You can't exactly do that, but what you can do is compare the farms to each other within their own context. And you'll see what I mean by that when we go, as we go through this. And then we'll go over some conclusions from the studies, prevention, and how you might be able to identify if you are having some artificial heat stress on your dairy. So heat stress is when the core body temperature of a cow rises above 102.2 degrees Fahrenheit, and as a result of the environmental temperature and humidity, the temperature humidity index. Artificial heat stress is when the cow's core body temperature is rising above that level because of the environment that we are putting her in. So if we're putting her in a barn and that barn is getting hot inside, hotter than outside of the barn, that is what we would call artificial heat stress. An important note is that barns do allow for an increase in the THI threshold for when cows will go into heat stress. So if you've got a high producing dairy cow, she might go into heat stress somewhere between 65 and 68 THI. By putting her in a barn, we'll increase that threshold to which she'll go into heat stress through having fans over her, soaking her, all our normal heat stress mitigation efforts. It's just when that threshold now that she has in the barn, when that's reached because we are not controlling that barn environment effectively. So, that can be a result of reliance on natural ventilation. We have natural changes in wind speed and direction, and you may not have the amount of air change or the velocity in the barn that you would think you would get from the wind. There could also be wind shadows, either buildings that are blocking the wind, or it could be natural windbreaks, lines of trees, just the natural topography of the area. And then the other part is if we do close barns and we don't design them with sufficient airflow, or we overstock them to a point where we no longer have enough airflow for the number of cows that are in that barn. We don't have good air distribution. So we're putting enough fresh air in, but we're not getting it to where the cows are. And of course, one of the big things with heat stress is we don't have enough velocity on the cows. If the air is fresh and it is the same inside as it outside, but we don't have any velocity on the cows, that's another cause for this. So a little bit of background on these case studies and the design of them. So there were 3 farms in this, all in eastern Wisconsin. Farm 1, it's a 1,150 foot long barn, 4-row tail to tail, 1,300 animals, 120% stocking density. The ventilation style, it's a tunnel vent barn, negative pressure tunnel vent with fresh air injection. So we're forcing fresh air in down the length of that barn on the sidewalls. We've got 36 air changes an hour and just over 1,000 CFM per cow. Farm 2, another long barn, 880 feet long. This is an 8-row head-to-head with 1,900 animals, 130% stocking density, traditional tunnel design, curtains on one side, exhaust fans on the other side, 33 air changes an hour and 890 CFM per cow. Farm 3, it's a shorter, more traditional tunnel vent barn, 450 feet, 6-row, typical head-to-head plus outside row layout. 500, it's understocked, 590 cows, and that's at 92% stocking density. Like I said, typical tunnel design, 45 air changes an hour. This one had really high 1,500 CFM per animal. We did the study. We were planned for the study to be when the THI outside was going to consistently be over 72 degrees. So we wanted it in that moderate or higher heat stress range at the peak heat of the day. This happened to be late June, early July. And what we did was we put environmental temperature humidity loggers, so temperature humidity hobo probes outside of the barns in a grassy area, away from blacktop. We put them at the inlet and exhaust end of the barns at the neck rail height. So it was very close to what the cows would actually be feeling. These were in PVC protective like covers with open ends on them, of course. Put them in the holding area as well, the entrance to the parlor and the entrance to the holding area. See what there was buildup down the length of the holding area. We also did internal cow temperature loggers. So this was just a temperature hobo. There was intravaginal on a blank cedar. Farm 1, we enrolled 16 cows, farm 2, 15, and then farm 3, 5 cows. They had a smaller population on that farm that met our requirements for what cows could be enrolled in the study. Sorry about that. During the study, also did daily observations multiple times a day. Stall usage, respiratory rate. We got samples of the resting area velocity. We looked at their water use for cooling, so available trough area for cows to drink from, and if they're using soakers, how they're using the soakers, settings, and are the soakers actually working. And then we also analyzed some herd records, looked at the daily average milk production by pen. We looked at milking times to parse out when were these animals in the parlor, when were they in the holding area, to see how that could affect their core body temperature as well. And we're only going to go over some of the results that we gathered. There's a lot of data from this. We're only going to go over the real pertinent part in this presentation. So, Farm 1. So this is an overview of Farm 1. Again, it's the long barn, tail to tail. It's the tunnel ventilation with fresh air injection. Exhaust is on the right side here. Your curtains are on the left, and you've got air being forced into the barn down the length. It's got panel fans over the outside row, and it's got 55-inch louvered fans over the inside row. We pulled cows for the study in this quadrant here. So wanted to make sure they were closer to the exhaust end so we could see if we're building up heat and humidity in this barn, the worst pen for it likely. And that was also the pen that happened to have the animals and the demographics that we needed for the study as well. So here's what we found when we were comparing the pen THI to the outside THI. So pen THI here is in blue, outside THI is in orange. So you can see that it was fairly consistent that the THI at the neck rail in this pen was the same as the THI outside. So we were not increasing the heat or the humidity down the length of this 1150-foot long barn. It did rise about 1 degree above the outside THI for some short periods on June 29th and on June 28th. We had some small areas here where it was warmer in the barn than it was outside. But it was, like I said, it's just about 1 THI point. You know, for reference, if you to increase the THI 1 point, it's about a half a degree increase in temperature and about 6% increase in humidity. So not much increase in heat and humidity, but it does increase that THI 1 point. This is a sample of some of the data we got for the core body temperature versus the pen THI. So the red line across here, that's the heat stress threshold for core body temperature. The gray background is the pen THI. These vertical black lines are the milking times that we got from the herd records. And then the blue line is the average core body temperature of the 16 cows on this farm. So you can see that after the peak heat of the day is when they are starting to peak in their core body temperature. And this was consistent across all days that we did this. Their peak core body temperature was after the peak heat of the day. And so you can see that they were rising above that heat stress threshold. And at this dairy, they were rising above that, that heat stress threshold most days. There was one day when they didn't, or 2 days when they didn't, and that was the first day and on June 28th. Every other day, they rose above that heat stress threshold, and that was at about 77 THI that they were starting to, that they would rise above it when they went there. But that inside THI was the same as outside THI, and it's a much higher threshold than typical for animals going into heat stress. Typically, again, for high producing animals, we're looking at somewhere between 65 and 68 THI that they start to go into heat stress. So if we look at the stall velocities there, they had great velocity, a range of 5.7 to 9 miles an hour, average of 7.4 miles an hour in the bed, so really good velocity. Typically, we would recommend minimum of 400 feet per minute, which is 4 miles an hour in the beds, and we're above that on all these counts. So we're good on velocity there. And the core body temperature we saw, it recovered quickly after that THI had decreased. So it wasn't lingering above that. It was once that had passed, it started to go down. Milking was not strongly associated with a rise or fall in core body temperature. It went one way or the other, and it wasn't consistent either way. An interesting thing that we found was that the core body temperature did rise, not necessarily above the heat stress threshold, but within 1 hour of milking, the core body temperature rose consistently. And that's likely cow gets done milking, goes back, eats, big meal, and then lies down, and that heat of fermentation is causing her core body temperature to rise. With the one day, and this is interesting, the July 2nd, which was the worst day of heat stress and the worst day that they went into above their heat stress threshold, is they went to the parlor, and after they got back, so they were probably done the parlor at around 8 p.m. here, and then at about 9 p.m. here, their body temperature started to rise, and it did go above that heat stress threshold because they hadn't come fully down yet. So it was just very interesting to see how that dynamic worked. So if we move on to farm 2, farm 2 is the wider, long barn. So 880 feet long, 200 feet wide, 8-row head to head. This farm, it's a typical tunnel ventilated barn, no fresh air being pushed in on the sides. They have curtains on the side walls and the end walls. Their exhausts are all over here on the right side of this screen. They've got 72-inch louvered fans over the head to heads, 2 per bay of stalls. They are overstocked at about 130%. And so their CFM per cow was lower than typical recommended. Typically the minimum is going to be 1,000. They were at 890. So they're a little low on that CFM per animal. They do have jerseys though, compared to the farm 1 was Holstein. So Jersey is going to be more forgiving in heat. So, the thought was, maybe even though they're a little low, it won't matter as much because they're jerseys. So again, this was the pen that we were looking at. This had the animals that we needed, right age, right demographics for what we were looking for the study. And so in this barn, when we were looking at outside THI versus pen THI, this is the same as the last chart. Outside is orange and pen is blue. And you'll notice in this one that the pen THI every single day is rising above the outside THI. So we are not keeping it the same THI as outside. It's what we are doing in the barn, how we're managing it, how we're controlling it. There is temperature and humidity rise in this barn. And you can see on June 28th, 29th, and 30th, the rise was 2 THI points, and it was for a fairly extended period of time too. It wasn't a blip that it went over. It was for the entire peak heat stress time of the day, it was rising 2 THI points. And as a reference, 2 THI points of rise is 1.5 degrees of temperature and 10% humidity, or 2 degrees of temperature and 5% humidity rise. That'll cause about a 2 THI point rise. So again, we're building quite a bit more heat down the length of this barn than we were in the last one. And this is again, sample of the data that we got from the core body temperature. This farm, you can see that these dotted lines here, the parlor software malfunctioned during the study, so we did not have exact parlor times. Parlor was on schedule, so we have approximate. Even with those approximate times, there wasn't any consistency in, again, rise or fall very much. And you'll see here on this day when it peaked, the THI in the barn peaked at 80, we did go into heat stress. And that was actually the only time they went into heat stress was when the THI reached 80. So they had great velocity in these beds, 8 mile an hour average, 4.5 minimum and 12.5 maximum. So great velocity in the beds on this farm. And like I said, core body temperature only went above the threshold when the THI rose to 80. It didn't go above, but it touched the threshold on the only other day during the study when the THI in the pen was 80, which was June 29th. So if we go back here to June 29th, when we saw that there was a 2-point THI rise and it went above 80, core body temperature on that same day touched that line, didn't go over it because it didn't go over 80 for as long as it did on this day. So it recovered quickly after the THI decreased. That's good because they've got good velocity, they're soaking, and milking, like I said, it wasn't really much here or there. It did in this farm, it tended to be associated with THI rise more than the other one, but again, it wasn't always. And like I said, the parlor software malfunction, couldn't get exact times in the parlor. And here we also did see, just like on the other farm, the core body temperature rise within 1 hour of milking. So again, just an interesting thing that we saw across all these farms. Farm 3, this was the shorter, more traditional sort of tunnel vent style barn. Typically like we used to have, don't tunnel vent a barn over 500 feet long. So this 450-foot long barn by 120 feet wide. Typical 6-row barn. This one had the lower stocking density, only 92%, and we had a really high CFM per cow, 1,500. This one is connected to another barn. The other ones were connected to other barns too, but this one was connected to a naturally ventilated barn through this breezeway here. We had curtain on the left side here on the sidewalls and the end wall. Exhaust was on the right side of the screen. And in this barn, we did not have any of the louvered fans. all we had 36-inch basket fans over the outside rows, and then we had 52-inch panel fans over the head-to-heads, but they were only mounted on one side of the head-to-head. So they were mounted over the inside head-to-head row. Well, I guess that would be, we'll call it the feed alley side of the head-to-head row. That's where the panel fans were mounted. There were not any panel fans over this side of the head-to-head rows. And again, we chose the pen that had the animals in the demographic that were in the demographic group we needed. And luckily, just as we wanted, it was on the exhaust side of the barn. So again, we'd be looking at the worst pens. In this barn, even with that great CFM per animal, we still saw this THI rise in the pen over the outside THI. So again, just like the last graphs, orange is outside, blue is the pen, and this is at the neck rail at the cow level that we see this THI rise. And this one was even worse than the last barn, and we were getting 2 points of THI rise for an extended period, 4 days of the study. So that was quite stark what we were getting in there. And it was reflected in the core body temperature of the animals. So these animals, they rose above that heat stress threshold every day of the study. And as you can see here on July 2nd, they really rose above that 102.2. The other animals in the other farms, they were only rising up to maybe 102.7. We went up to 103.8. So it was fairly rough in this barn. And unfortunately, this parlor software also went down during the study. And so it was also behind. So we didn't even have approximate milking time. So we weren't able to correlate anything with any of the holding area data that we got. And you can see, though, again, I mean, here we rose above 2, but it was if the THI in the pen was above 77, they were going into heat stress. And you can see here that most, except for June 28th, every day, the THI in that pen was above 77. And so they were going into heat stress, and they were going fairly far into heat stress. So in this barn, great CFM per animal. We had an average of 3.6 miles an hour in the beds, but we had a minimum of 0, and we had a 9 mile an hour maximum. And with a 9 mile an hour maximum, but only a 3.6 average, we had a lot of readings that were really on the low end, that were below 200 feet per minute. 200 feet per minute is the minimum cooling airspeed, not the recommended, just the minimum, that you don't get any amount of cooling until you get to 200 feet per minute, or about 2 miles an hour. And you really get the best when you're 400. You want 400 to be what you're getting in the beds. And this was below that on average, and most of them were below the 200. So we did not have good velocity. In fact, I know the 9 miles an hour velocity that we got was in a bed where the basket fan was pointed down into the bed. Core body temperature rise was severe. It persisted for a long time. And like I said before, parlor software malfunctioned, so we weren't able to look at anything with milking times here. So what do we conclude from this? Like I said, can't compare directly farm to farm, saying farm 2, cows only went into heat stress once. Farm 1, cows went into heat stress most often, and so did farm 3. So therefore, farm 2 is the best. You can't do that because, like I said, they're different animals. Farm 2 and farm 3 are Jerseys. Farm 1 are Holsteins, different feed, but we can compare them within the context of themselves. So did the inside THI equal the outside THI? That's the main thing that we're looking at in this discussion here. And that only happened at farm 1. It didn't happen at farm 2 or farm 3. And so that heat stress that the animals felt was because of what we were doing. If we had better ventilation, better cooling, and we did not cause that THI rise, and the inside THI equaled the outside THI, at least in farm 2, we would not have gotten the animals going into heat stress. That's what I'm calling artificial heat stress in this context. And so what do we have at farm 1 that's helping us keep that inside THI the same as the outside THI? Well, we've got greater than 1,000 CFM per cow, but we know that isn't the only thing, because farm 3 has 1,500 CFM per cow and they still were going into heat stress. We've got velocity over 400 feet per minute, had that at farm 2, didn't have that at farm 3. Inlet was in the proper location at all farms, which is always a good thing, making sure that you have your inlet properly designed in the correct location. The inlet is controlled in tandem with the exhaust on farm 1, and it's not on farm 2 or farm 3. And that's a big deal, making sure that those are controlled together and not independently. And also on farm 1, short circuits are minimized, not at farm 2 or farm 3. Like I said, farm 3 is connected to a naturally ventilated barn. So those exhaust fans, when they're pulling, they can pull right out of that naturally ventilated barn rather than the curtain. That fresh air is coming from somewhere that it's not meant to. Same with farm 2. Farm 2, it's connected to the parlor on one end. It can pull, connected to the holding area. It can pull out of the holding area. It's not necessarily pulling through the curtains where it's designed to, because it's connected to something else. Farm 1, it is connected to other barns and it's connected to the holding area, but the short circuits are minimized because the one barn it's connected to is power ventilated in the exact same style, and the holding area and parlor are also power ventilated. So we're not pulling from anywhere that it can easily pull from, like a naturally ventilated barn. We're also pushing in fresh air injection down the length of that barn. So we don't need as much pull down the length of that barn as we would in something you're just trying to negatively pressure and pull through curtains. So farm 1, while the cows went into heat stress, their ventilation system controlled the environment the best. We had the sufficient CFM per cow. We had the fresh air injection down the length. That fresh air injection was also purposefully designed so that when it got pushed into the barn, it was redirected into the beds. Like I said, those temperature humidity probes were at the neck rail height. So in those other barns, you might have been able to go into the feed lane and not see any THI rise. But that doesn't matter because there are no cows in the feed lane. We want them in the beds half of their day. So that's where we want to make sure that we don't have that THI rise. In farm 1, it was purposefully designed so fresh air was put into those beds. Louvered fans over the beds gave sufficient velocity to the fresh air. The short circuits were minimized, so we're not pulling from hot parlors and holding areas. We're not pulling from manure flumes. We're not pulling from other barns. And the demands of the exhaust are reflected in the behavior of the inlet. So if the exhaust needs more inlet, the inlet opens more to satisfy that exhaust. If it doesn't, closes or fans slow down. We're making sure that everything in the barn is controlled together and working together as opposed to possibly against each other. Farm 2, the cows did well, but as we saw, THI rise in the barn rose to a level to put the animals into heat stress when the outside THI, based on previous days in the barn, when the barn THI rose to 79, the cows didn't go into heat stress. The day they did go into heat stress, outside THI was 79, inside the barn was 80. So they could benefit from being able to control that THI better. So it could be either from better CFM per cow, which could be, not overstocking as much, could be adding in some more exhaust fans, or it could be with adding in some fans for some fresh air injection down the length of that barn to get that fresh air down into the beds. Because again, remember, we want this in the beds where the freshest air is without the THI rise. And again, the interesting thing, farm 3 had the best CFM per cow, so you would assume there wouldn't be any THI rise, but it had really poor performance overall. It didn't have good velocity in the beds, and you had THI rise, and the cows there went into heat stress the worst. And really that's a function, the recirculating fans were completely insufficient. Half of the basket fans were not working, and there's unimpressive velocity elsewhere in the beds. The panel fans, they were only on one side, they weren't angled properly. And so you were only getting good velocity in very few beds. So there was no redirection of fresh air into the beds because they weren't angled downward enough. And half the basket fans aren't working. So even if you are bringing in fresh air, as it comes in from those curtains and starts to rise up over the stalls, because they're an obstruction, so the air will rise up over them, there's nothing to push the fresh air back down into the beds. So that's why our temperature humidity in the probe in the beds was seeing that rise in THI. The other thing, it's connected halfway to another barn and it's short circuiting the inlet curtains. So you're pulling heat from another barn into your barn halfway down rather than pulling fresh air from the curtains down your barn. So you're just adding more heat to your barn down that length. And that's, again, we could benefit there from doing some better things to control the short circuiting, injecting fresh air in. So main conclusions from this would be that, heat stress, it's not preventable, but what we can do is minimize the possibility that the animals are going to go into heat stress. With proper ventilation design, we can increase that heat stress threshold, and we can make sure that we're not artificially raising the THI in the barn above what the outside THI is. Another thing we found is that no or minimal THI rise is possible in a barn that's 1,150 feet long, which is a little bit more than double what the old rule of thumb was, which was don't tunnel ventilate a barn that's longer than 500 feet. You'll have too much heat and humidity added. And we found that no, we can do that properly. And we found that all aspects of a proper ventilation system are necessary. Minimum of 1,000 CFM per animal, minimum of 400 feet per minute, which is 4 miles an hour in the beds. Proper inlet design. If you're designing the inlet, think about where is the air going to enter? How is it going to be distributed into the beds? And is it enough to properly feed the exhaust fans? Make sure it's controlled in tandem with the exhaust fans so that what the exhaust is calling for can be met by the curtains. And think about short circuits, manure flumes, connections to other barns. If it's a naturally ventilated barn that you're putting exhaust fans on, how much are those curtains, if you don't put polycarb on, you just use the old natural vent curtains and nail them up, are there any gaps in that? How much air could leak through that and short circuit the curtains on the end wall that you mean for all that air to come through? So a lot will go into this to making sure that you're doing the best that you can for the ventilation design to prevent THI rise in the barn. So to identify it on your farm, it would be a bit of an in-depth process even without, an in-depth study like we did. So the way you would do it is if you know you're going to have days where you're going to have heat stress that's in the moderate range, so greater than 72 THI. If you've got a handheld temperature humidity meter like a Kestrel, some of them just do temperature and humidity. There are models where it will actually directly read out THI as well. Those ones are more expensive. But if you go into the pens in the barn, into the beds, because we want it where the cows are, record multiple locations over multiple days, what the THI is in the beds. And you have, like I said, you have to do it over multiple days and likely multiple times a day, because a single reading could just be aberrant and not mean anything. You want to make sure that it's consistent over time. And if it is consistent and it's consistently above 1 point of THI than the outside THI, then you have a potential issue. One is not a hard and fast cutoff. In my professional opinion, one is about where you would start to think, this isn't just an error in measurement. This isn't, I didn't wait long enough for the probe to calibrate to this new position. It was in my pocket. If it's greater than 1, it's likely something's going on. And the greater that difference is, the more likely you have an issue. If it's 1.1, maybe, maybe not. If it's 1.5, 2, 3.5 rise in THI points over outside, then there's going to be a potential issue. Determining the actual effect on the animals with non-invasive techniques. So, okay, you got THI rise in the barn. Well, if it doesn't affect the animals, is it an actual issue? So if you want to determine the effects on the animals with non-invasive techniques, that requires a much more intensive investigation. You want to make sure you're tracking dry matter intakes before, during, and after periods of heat stress, daily milk weights. You would want to make sure you're looking at respiratory rates in the pens where you measured that THI rise. You would also want to make sure not just, I found I have a THI rise, now I'll look at the cows. You still want to be measuring the THI in the pens in those same spots when you're also looking at the animals. So like I said, respiratory rates, stall use, and you want to do it over time, making sure with repetition, there aren't any aberrant readings. So you can do it. It is intensive, but if you do notice, again, it feels kind of warm in the barn, feels stickier than outside, feels warmer than outside, check the pens, check the beds. If it does feel that way, you might want to start looking into this because heat stress is costly. So do we have any questions?
Yes, we have a couple of questions. First of all, thank you very much. That was great. When you calculate the CFM per cow on these tunnel vent barns, do you use the sum of exhaust and circulation fan CFM?
No, only the exhaust fan CFM, because the CFM per animal is based on the amount of air changes. Circulation fans do not change air. They move air through the barn and give velocity. It is based on the air changes. So it's only exhaust fan CFM.
Perfect. And then in hot and humid climates, would you think that barn length will still have a minimal effect on THI, or would that increase?
Yeah, in hot and humid climates, it's going to be likely that you may have to go shorter with the barns. I've been in some barns in some hot and humid areas that have a tunnel vent with some fresh air injection and louvered fans over the beds, and they do better than the ones that didn't have the fresh air injection, but they weren't nearly as long as this barn was. They were only, I think, probably 650 feet long, so about like 200 meters. So they weren't, again, they weren't quite as long. Again, even at 1,150 feet, there is always going to be an upper limit as to what you can do. And so, but in hot and humid climates, you will likely have a shorter upper limit than you may in the upper Midwest, like here.
And did these barns have any type of evaporative cooling, like misters or sprinklers?
They all had feedline soakers. They did not have high pressure fogging to drop the air temperature, just sprinklers at the feed line.
Perfect. So why is it important that the inlet be controlled in tandem with exhaust fans?
So it's actually, it's really important that happen, because the way air is brought into a barn is dependent on the static pressure in the barn if you're bringing it across an inlet curtain. And you don't want the static pressure to be too high, because you'll put undue stress on the exhaust fans and lower your CFM, but you don't want it to be too low, because then outside air patterns can completely change how air comes into your barn. it can come in on a diagonal, or it can actually be sucked out of the inlet of the barn if the inlet is too open and the static pressure is too low, which I've seen. So what you want is an inlet that is going to be open the correct amount to get the correct static pressure for the exhaust fans that are running at that temperature. So a traditional style curtain that just kind of opens based on time is not going to be precise enough to be able to work with the exhaust fans properly. And it's the same with garage doors. You know, if you open a garage door is open or closed, and it can't be automatic. So someone needs to be there to make sure it would be open the correct amount for the number of exhaust fans that are running. And it just, relying on a non-position controllable curtain leads to issues all the time.
Do you have any idea what the static pressure was in that 1150 barn, and how do you calculate it?
You can, well, one, you can measure the static pressure with a differential pressure meter. You can also calculate it based on the cross-sectional velocity. The issue with the cross-sectional velocity, though, is that is partially assisted by the fans over the beds. So really, to calculate it from the cross-sectional velocity, you would need to know what is the pure contribution from the exhaust fans and versus the recirculating fans. I believe in that barn, don't quote me on this because I do not have it written down in front of me right now. I believe at the exhaust end of that barn, the static pressure was about 0.08 to 0.11, somewhere in that area. Again, they do fluctuate with outside wind patterns, but that was roughly what it was.
Thank you very much. So I'm not sure what this question is, Tom, but how do we utilize more algorithms? Could you be a bit more specific? Or do you understand what he's talking about?
I do understand what he's talking about. You know, there are a lot of algorithms built into these control systems to make sure that what's going on in the barn is correct for the temperature in the barn and what the cows need. So that's built into these control systems.
Wonderful. So I'm just going to give it another minute. If there are any other questions, feel free to send them in. But while we're doing that, I'd like to invite everybody to join us back on June 18th for optimizing the use of sex semens in dairy herds. That is our next webinar by Dr. Paul Frick. And I would like to say thank you very much. This was a great webinar. And if you have any other questions, you can contact us at marketing@VES-Artex.com and we will pass them on to Dr. Brady. So thank you everyone for joining us.
Thank you.